Welcome to lecture number 39. So, till the last lecture, what we have done is the importance of the single molecule spectroscopy, right? And we have shown that what kind of extra information single molecule spectroscopy can give. And we also have seen that the small observation volume is essential to get the information of a single molecule. So, now question is that how to achieve such kind of small observation volume. As you remember, I said that if you take one rhodamine 6G molecule in 1 ml of ethylene glycol, one of the solvent, right, then if the intensity of the fluorescence is 1, then the intensity of the Raman scattering by ethylene glycol molecules, that 1 ml of ethylene glycol molecule would be 10 to the power 10. So, obviously, you will not be able to see this 1 intensity of fluorescence in front of 10 to the power 10 intensity of the Raman scattering. But if you take one rhodamine 6G molecule in 100 femtoliter of ethylene glycol, then this intensity of the fluorescence and intensity of the Raman scattering will be very similar to each other. And if you now take one rhodamine 6G molecule in 1 femtoliter of the solvent, here it is ethylene glycol, then in that case the fluorescence intensity will be 100 times more than the background Raman scattering, and in this case you will be able to see the fluorescence from the rhodamine 6G, because this is a single molecule. So, the number of photons which are available from the single rhodamine 6G molecule is very, very small. So, your background has to be small. More importantly, your solution, right, has to be diluted enough so that only the small observation volume is not enough. Your solution has to be diluted enough so that this 1 femtoliter observation volume contains only one molecule of rhodamine 6G, right. If you put many of them, if you increase the concentration, then probably in that 1 femtoliter observation volume will contain more than one rhodamine 6G molecule, then you will lose the single molecular level detection capability. Now, the question is that how we will going to get this small observation volume which is 1 femtoliter, right. So, if you consider a box like this way, let us say it is a cube, right, and if each side is about 0.5 micrometer, right, then approximately the volume what you are going to see is about 0.1 femtoliter. Right. So, you need similar type of dimension to be achieved, right. And so, now today we are going to discuss how to achieve such kind of small observation volume. The first technique which I will discuss is based on total internal reflection method. Total internal reflection method, and this what we know that if I have two medium, one with refractive index n1, other with refractive index n0, and then if I have incident light falling on this through medium with refractive index n0 towards the medium with refractive index n1, and if this incident angle theta I is greater than the critical angle. So, if theta I is greater than theta C, which is defined as sine inverse n1 by n0, then there will be total internal reflection, right. So, the beam will be reflected in this way. So, this is my total internal reflection. All the incident light will be reflected by the total internal reflection if it satisfies the total internal reflection condition, but still what you are going to see is that one evanescent field around this region will be generated. Evanescent field around this region will be generated. So, this is nothing but a near field standing wave, right. Just write here near field standing wave will be generated, which is known as evanescent field, will be generated to the medium with a refractive index n1, right. So, you are going to get field out of this. Now, the strength of this evanescent field, right, actually decaying as you go away from this interface. Suppose this is your interface and this is your total internal reflection, and this evanescent field will be generated here, but the strength of this field will exponentially decay as you move from the interface to away from the interface, right. So, this evanescent field strength, right, decay exponentially, and that can be written like this way. So, e to the power minus z by d. Obviously, it will start with some initial value of this field. Let me write this is I is 0, and which is the electric field dependence as you move from away from the interface. So, here is my z, right, and in this case my variable is obviously this z, and d is given by, where d is given by lambda by 4 pi n0 square sine square theta. So, this is my incident angle. So, theta I should write minus n1 square to the power minus half, right. So, for example, right, if let us say, let me consider this n0 is equal to, let us say 1.5, some type of glass, let us say this is 1.3, this is like water. So, I can readily calculate the theta c value from here. So, here theta c I can calculate, theta c will be around 60 degree, right. So, if theta I is greater than 60 degree, right. So, let me consider that theta I is equal to 70 degree. I can choose that which is greater than theta c, then it will fulfill the total internal reflection condition. In that case, right, I can simply evaluate what is the value of d, right, because I know n0s, I know theta I know theta, I know n1, but you see it also depends on the wavelength. So, I fix a value of wavelength. Let us say for this case the value of the wavelength of the incident light is 600 nanometer. So, if you plug in all these different value, what you are going to see is the value of d, and if you calculate this, you will get this value of d as 73 nanometer, right. So, you see this is d is 73 nanometer, and this d is over here, right, d is over here. That means the intensity or the strength of this evanescent field will decrease exponentially, right, and it will be almost 0 at 4.5 times of this d value, right. This is the nature of this exponential function. So, what I want to say is that this evanescent field strength is high here, but this evanescent field will going to be 0 exponentially. see this is my exponential function, right? And do not forget that this is a symmetric, right? This is symmetric like this way, right? So, evanescent field strength is very high and then it is going to be 0, right, as the Z will increase. So, I can simply tell that E Z, right, will be almost 0, that means field strength is finished at a distance Z equal to 73 into 4.5 nanometer, which is roughly equal to 330 nanometer. So, I can simply write. That means ultimately what you are going to see, you are going to get a I can describe this as roughly I can describe this as type of cone, right, where this spot, this is a spot, this is a circle, right, this is the spot size of the incoming beam, right. Here that spot size whatever I have shown is little tiny, now I am expanding it. So, now the laser, the light, excitation light, it is actually laser. So, this excitation light is coming like this way, this is important, let me show you. So, then here is your, sorry, this is incident, right, and then reflected like this way, reflected back under total internal reflection. So, what you are going to see is this is your spot size, and because of this you are going to get this evanescent field. Evanescent field will decay exponentially like this way, this is your evanescent field. That means above this interface, the place where, right, this field exists, this field does not exist below the interface, above the interface the field exists in this region. So, I have just assumed that this feature, right, this exponential decay will be like a cone. Now, if the diameter of this excitation light is known, right, then you know this diameter, right, and you know how to calculate the volume of this cone. So, volume is equal to 1 over 3 pi r square h. So, if I say the diameter of this incoming light, right, is let us say real number. So, let us say it is 10 micrometer, right, and 10 micrometer I can create. So, if it is a 10 micrometer and then this 10 micrometer light will come here and it will undergo to total internal reflection like this, but this evanescent field will create. So, then the radius it will be 5 micrometer and this height will be, I just have roughly calculated it, around 300 nanometer. So, height will be around 300 nanometer, right, or 0.3 micrometer, right. So, using this formula you will be, so here is my just situation that 600 nanometer light, 600 nanometer light is making such kind of thing. For the 600 nanometer I have calculated what is the value of this height is about 300 nanometer, and with that I want to calculate the volume. If you plug in all these values over here, then what you are going to see that volume is 7.8 femtoliter. So, see, just by taking this total internal reflection condition, you can achieve the observation volume of 7.8 femtoliter. Now, let me show you that experimental setup in this case. Like if you use such kind of device, right, this is made of special type of glass, that is what I said, this is the refractive index in your N0 is equal to 1.5, and let us say you have set up your experiment by putting a sample cell over here. This is your sample cell, it is somehow attached. So, if you have a sample, right, water solution of your sample, so water solution is present throughout this sample, right, and you make a sufficiently dilute condition so that your fluoropores, right, your fluoropores are present throughout, but in the sufficiently diluted condition, right. These are your fluoropores. Obviously, these fluoropores will undergo a Brownian motion. It can come from here to here, it can go from here to there, they are in motion, right, all the random motion. But now, if you use an excitation light, let us say this is your excitation light, and you are creating your excitation light like this. So, the diameter of this incoming beam is not very high, because you want to achieve smaller volume. If this diameter is high, then the volume will be high, right. So, you do not want that, you want to achieve a smaller volume. So, you want a very tightly collimated beam, and that will going to be reflected, that will be going to be reflected like this way. So, if my drawing is okay, it will be like this. So, here is your incoming, here is your outgoing after total internal reflection, right. And what you have? You have created this evanescent field like this, right. So, only when your fluoropores are present here, then only you will going to see the fluorescence, right, because this part of your sample, I mean, there is no one to excite. Here evanescent field having the similar wavelength of the excitation of this incoming light will be able to excite your fluoropore. Then you will get fluorescence only when your fluoropore will present inside this small observation volume. When the fluoropore is present here, they are dark, they are not fluorescing, and when the fluoropore is present here, so you will get the fluorescence, otherwise not. So, by this you can achieve this small observation volume. The next one, to achieve this small observation volume is another method. The next method is called the confocal detection method. Confocal detection method. In this case, what we do is that we use a lens, right. Let me draw this lens over here. Lens, and this is your incoming excitation light, and you tightly focus this incoming excitation light to a very tiny spot, right. Best you can do is the diffraction limited focusing. The size of the spot is diffraction limited focusing, and that you can do with a laser. So, in all this experiment, right, to achieve the small observation volume, right, the light source what is being used is the laser, because for the conventional light source you cannot focus so tightly, right. So, in this case you will get diffraction limited focusing. Now, this is very much applicable. Now, if I show you the another version of this geometry, it looks something like this. Suppose you have this lens over here, and your incoming beam diameter is this much. So, anyway, this will going to focus, right. So, if the color of this laser is, let us say, blue, so this part is blue, and here is your blue, right, and here is your blue, right? That is the light, right? Now, if you zoom out this part, what you are going to really see is the following. Correct? And again, this is your this is your that light. So, in the focal plane, right, the diameter is this much, is your diameter, right. But if you do same thing, same lens if you take, and in this case let us say incoming beam of the same color, the diameter of the incoming beam is much more than this, obviously it will again going to focus, focal length is similar, so it will focus in the similar position, right, like this way. So, here the incoming beam is like this is your incoming beam, and here is your beam, and here is your beam, right. Now, if I zoom out this part, what you are going to see is that it looks like this, right. So, here you see the spot size at the focal plane is much smaller than this, but it is diverging too much. So, here if I again color it, so this is your excitation light, this is your excitation light. Now, if you consider this is your excitation light. Now, if you consider that your molecules are present only at the focal plane, so condition if I impose is the following, that the molecules which is under investigation, right, are present on a plane, and that plane is this focal plane in this case. So, in this case, if you have molecule here, it is not visible, if you have molecule here, it is not visible, if you have molecule here, it is not visible, but if you have molecule here, it is visible, because it is focusing only at this focal plane. It is not visible, it is not visible, it is not visible. So, you can create a tiny spot, right. That tiny spot depends on many things, basically the numerical aperture of this focusing lens, and you will get a very tiny spot. But you cannot apply this thing to the solution, because in solution, let me draw another setup for you for the solution case. Let us say you have a sample stage like this, and your that special lens which is called the objective lens is present over here, right, and you are having a incoming light overfilled to the objective lens, and then this will going to focus, right, and this will going to focus it like this way, right, and your sample is present over here. Here the whole position is your sample position, right, your sample is present over all along over here, right, on top of this sample stage, and this excitation light, let us say, is like this. This is your excitation light, this is your excitation light. So, it will going to focus like this way, isn't it? it is going to focus like this way. Now you see all over this region, starting from here to here to here to here, all over this region the molecules are being excited. If the fluorophore is present, if the fluorophore is present here, if fluorophore is present here, they are not excited, but if the fluorophore is present here, it is excited, it is going to give fluorescence, it is going to give fluorescence, this is going to give fluorescence. If the fluorophore is present here, this is going to give this will not going to give fluorescence. If it is here, it will not, right. So in this case, you are going to see the fluorescence from the entire region, right, and obviously then that means your observation volume is really large. If you now decrease the concentration of the molecule in the sample, but your observation volume is more, right, that means your background Raman scattering will be much more. So your aim is not fulfilled. That aim is to create a small observation volume. When it was just a thin layer of sample which is present in only 2 dimension, then obviously there is no problem. I can achieve the small observation volume because nothing was on the top, nothing was below that plane, right. But in this case many molecules are there, especially the sulfate molecules. So the observation volume is important in this case. That can be achieved by this confocal method. What is this confocal method? For this I have one animation. So here you see this particular molecule is shown over here, which is colored as yellow, like this molecule will start diffusing, right. So you look at here, once you excite with your excitation source, as I said that most of the case this is the laser. So this is focused with this special type of lens. I said this is my lens, special type of lens called the objective lens, and it will be focused on the sample. So in the sample position, this is my sample. In the sample position, the excitation light will look something like this, right. Now once this molecule will come in this green region, once the molecule will come inside, here is also sample, this is sample, because sample is large, right, but this excitation light is only present, right, in a smaller region within this sample, right. So in this case, when this molecule will come and enter, you are getting a fluorescence, right, and you see the fluorescence can come, and when the molecule will go out of this excitation region, then there is no fluorescence. But when the molecule come in over here, again the molecule show the fluorescence, again molecule come in, it is showing the fluorescence, and so on and so forth. Okay, as time is up, let me finish over here and we will continue our discussion on the next lecture. Thank you very much.